Third talk in this morning's session is from Professor Frank James from London's Royal Institution on electric paradigms from Volta to Maxwell. Professor James.
Thank you. So this is the mission statement for the meeting today. The history of physics can be viewed as consisting of major paradigm shifts followed by decades and even centuries working through the consequences of the dominating paradigm. And this will Lieber put that up, followed by the piece on Copernicanism. But since I'm not talking about Copernicanism, I didn't put that up. What's striking about this is it omits where the notion of paradigm comes from. That's Kuhn's Structure of Scientific Revolutions, published in 1962. And like all texts, it has a context in which it was brought into existence. And there are lots of contexts in which the structure plays into. The Cold War, for example, the whole two cultures debate in this country, which was already in full swing by 1962. I don't have time to talk about those. Maybe we can talk about it in discussion. I just want to talk a bit about the term scientific revolution first. It sort of pops, so the earliest I've come across it, and there may be earlier versions, is actually in Humboldt's Cosmos in the 1840s. But in our terms, it really begins with Herbert Butterfield's Origins of Modern Science, published in 1949, where he says, the scientific revolution outshines everything since the rise of Christianity and reduces the Renaissance and Reformation to the rank of mere episodes, mere internal displacements within the system of medieval Christendom. This term was then taken up by Butterfield's protege, Rupert Hall, in his book, The Scientific Revolution, 1500-1800, The Formation of the Modern Scientific Attitude. Science is the one product of the West that has had decisive, probably permanent impact upon other contemporary civilizations. Compared with modern science, capitalism, the nation state, art and literature, Christianity and democracy seem regional idiosyncrasies whose past is full of vicissitudes and whose future is full of dark uncertainty. It's a really nice pessimistic bit, which is quite typical of Hall's work at the end of that. So you had the scientific revolution, well entrenched by the mid-1950s, and then you had things like the Copernican revolution, about which Kuhn wrote. You had the chemical revolution, that's all written about by the close. So all sorts of revolutions in the nature of science were kicking around in the 1950s and early 60s. And indeed, one has to remember that C.P. Snow's Two Cultures essay was titled Two Cultures and the Scientific Revolution. By that, he didn't actually mean any of the 17th century revolution. He meant the revolution in modern science associated with Harold Wilson's Scarborough speech to the Labour Party about the white heat of the technological revolution. But Snow, being Snow, read that as science rather than technology. That's Snow for you. And as Lieber has pointed out very well this morning, Kuhn's Copernican revolution has really been overtaken by lots of recent work that she described in understanding what happened in the Renaissance. Nevertheless, what you then have is Kuhn taking all these revolutions in sort of the general science area and creating something called scientific revolutions, which have a structure. And that seems to me a really rather physicist's way of approaching the issue. You have a phenomenon out there called scientific revolutions which occur in various contexts. Because they're called revolution, they must have some sort of structure in common. And that's what Kuhn does to try and bring the revolutions together into some sort of coherent whole. And that's where the notion of paradigm comes from as a mechanism of explaining why you get these alleged switches in knowledge over time. This problem I have with Kuhn, now Kuhn was actually clearly very, very successful, as Rob said, in what he was writing in the 1960s. But that's in the 1960s, where our knowledge of the practice of science, the material culture of science, all the things that historians like me go on about at great length today were simply not there, or if they were there, in a really minor way. Experiment, for example. Yes, everybody realized, Kuhn realizes that experiment was important, but experiment is always seen as subservient to theory. I mean, and this is particularly explicit in the work of Karl Popper, where he says experiments are designed to falsify theory. And it's really not until the sort of 1980s, with the work of people like David Gooding, who studies on Faraday, which is why I put Gooding up particularly. There are lots of others who saw foreground experimentation, realize that experiment is capable of producing knowledge in and of itself. It's the equation of theory equals knowledge, scientific knowledge, it simply does not become sustainable from the 1980s onwards in historical literature. So while Kuhn could have been a perfectly satisfactory theory for the 1962, over the sort of intervening following 20 years, 30 years, as historians work much more in the detail of what goes on in science, the practice of science, the experimentation of science, what people actually do in laboratories, not to mention all the institutional contexts in which science is operated, or political context in which science is operated, we get to a rather different story where a Kuhnian version becomes really rather difficult to sustain. And this concentration on theory is seen very clearly in what I'm going to talk about now, which is sort of electricity. One of the great things about modern technology, you can count the number of words that people use in a book. And if you look at what Kuhn talks about from Volta to Maxwell, Volta gets 1 mention, Davy gets 0 mentions, Faraday gets 1 mention, and Maxwell 24. So basically, Kuhn is concentrating on the theory of physics, not on the practice, not on the experimental nitty-gritty. Which again, I think is fine for the 1960s, is not fine for today. Kuhn actually uses the word electricity about 220 times, if I recollect correctly, but that mostly means static electricity, and not what I'm going to be talking about today, which is voltaic electricity, discovered, invented by Alexander Volta in the late 18th century. Basically, a pile of different types of metal, discs of metal with some sort of paper, acidified paper, to create an electric current. This is Volta demonstrating it to the first consul Napoleon. And one of the things I also want to emphasize is that, again, the history of these famous people is because they are famous, and that therefore they get lots of iconography and publicity. And this is a really well-known image. It exists in hundreds of editions at any rate, so coming from Florence originally. The precise pile on the right, by the way, is my favourite object in the Royal Institutions Museum. It's the pile that Volta gave to Faraday when they met in Milan in 1814, and I'd like to see it metaphorically as the inventor of electric battery, at least the Canon torch of electrical research, is the battery part of it, for Faraday to continue work into the 19th century. And this was celebrated in 1927 to mark the centenary of Volta's death. There were enormous celebrations held in Italy. The joint honorary presidents of the Volta commemorations was the Italian dictator Benito Mussolini and the Irish-Italian engineer Guglielmo Marconi, a member of the Grand Fascist Council, by the way, in Italy. And the celebration was held in Como. It's a nice place to have a celebration, I have to say. The meeting was attended by 12 Nobel Prize winners and cost 13% of the entire Italian higher education budget for 1927. So really famous, really being celebrated, but glorifying fascist Italy, obviously. So going back to Volta, this is the first page of Volta's paper, which he sent to Joseph Banks, President of the Royal Society of London, for publication. The paper was in two parts. One part went by post, by Hamburg, because of the war. The other part went by a merchant, and there was sort of several months' delay in delivery of the paper, which caused problems. And Volta, in this paper, wonderfully illustrates the principles of electric pile in his diagram. And it's published when both parts arrive, in French. I can't imagine modern philosophical transactions publishing a paper in French today. But because of this sort of problems of delay, rumours is published in newspapers, in sort of other scientific periodicals before the official publication, and rumours reach Bristol in the middle of 1799 of this wonderful new invention that's been made in Italy, and it's taken up by Thomas Beddoes on the left, head of the Medical Pneumatic Institution in Bristol, and Humphrey Davy, who's the superintendent of the Medical Pneumatic Institution in Bristol, and they start working on this wonderful new phenomenon. Davy actually coins the word battery. Up until this point, this device is called the pile. But Davy, in this 1799 work, starts using the word battery to denote it. And Davy, the only way of detecting electricity in those days was passing it through a frog. And so Beddoes ordered 300 frogs from Shropshire, where he came from. And when they arrived, a government agent provocateur, because Beddoes was under surveillance by a Home Office secret agent. Think of words from Coleridge a few years earlier, being chased across the Contocks by a government agent, and government agents were all over the place against suspected seditionists like Beddoes. Beddoes had actually been reader in chemistry in this university, but because he's a Jacobin and a Democrat, he was asked by the Vice-Chancellor to depart to Bristol, which is what he did. When these frogs arrived, this government agent provocateur put it around that the reason why Davy and Beddoes needed these frogs was to feed an invading French army. Paranoia and xenophobia in one go. That worried Davy, obviously. Even more worrying, the following month, the Anti-Jacobin Review, a pro-government newspaper, think Daily Mail, only worse, wrote a coruscating attack on the work of Davy and Beddoes. And at that point, Davy decided to leave the leave Bristol to move to the Royal Institution, which is a quite remarkable flip-flop, one has to say. He's moving from radical provincial Bristol to conservative imperialist Royal Institution under Joseph Banks, who loathed Beddoes, to put it mildly. There's a wonderful letter that Banks writes to Georgiana, Duchess of Devonshire, criticising Beddoes. It's about as close as a gentleman could write about one gentleman without transgressing the etiquette of writing to a duchess. It's a quite extraordinary letter. Anyway, at the Royal Institution, Davy had access to the big batteries that were being built, mostly by William Cruikshank in Woolwich, but also with components by Wedgwood. And this is the battery he had in 1807, with which he was able to isolate sodium and potassium, and ultimately identified or discovered 7 other chemical elements. The result of all this work was that in 1812, after he'd retired, having married a very wealthy widow, Davy wrote his Elements of Chemical Philosophy, which argued that basically what we know as chemical affinity, how chemicals stick together, was due to electricity. Is that revolutionary? I'm not entirely convinced. I think it's just a sort of, it emerges from the sort of experimentations, the sort of playfulness and enormous manipulative skill that Davy had in developing his work. And like Volta, Davy became incredibly famous. He nearly had a 100-foot column built above Penzance, where he was born. They didn't have enough money for that. But Davy is displayed in the Natural History Museum in this city as one of the statues of the great savant of the time when the museum was built in the 1850s. Well, one of the results of Davy marrying a wealthy widow was he could retire from being Professor of Chemistry at the Royal Institution at the age of 33, which I think I envy even more as time goes on. And sitting in his last set of 4 lectures given at the Royal Institution was a young bookbinder's apprentice, Michael Faraday, who just was about to finish 7 years learning how to be a bookbinder, and he decided, for reasons which are still very opaque to me, instead of pursuing a safe career as a bookbinder, where I'm sure he'd been very successful and earned a perfectly reasonable income, he decided to move from bookbinding into science, and in particular chemistry. He attended Davy's lectures, sent Davy his notebook asking for a job in science, which was not going to be anywhere near as well paid as doing bookbinding. And after a sort of really complicated set of contingent circumstances, Faraday was appointed laboratory assistant in the Royal Institution and worked his way up the hierarchy to become the first Fullerian Professor of Chemistry in 1833. Faraday's major opportunity to do original scientific work followed the discovery in 1820 of electromagnetism by Hans Christian Ørsted. And again, somebody else who's also portrayed, his statue also appears in the Natural History Museum in this city. From this work, Faraday discovered the phenomenon of electromagnetic rotations. There's only 4 pages of notebook where Faraday describes how he did that, make that discovery. David Gooding's, virtually the entirety of David Gooding's book, Experimental Making Meaning, is concerned with unpacking those 4 pages. I mean, David actually built his entire career understanding those 4 pages and showing the power of experiment to generate knowledge. There was a slight problem, well, it was actually quite a big problem with this, because Davy, who was always jealous of anybody who's like competition, claimed from the presidential chair of the Royal Society of London, which he'd become after succeeding Banks, that his good mate and fishing companion, William Hyde Wollaston, had actually discovered rotations first, or if he hadn't discovered rotations first, Faraday based his own work on Wollaston's without acknowledgement. And he said this from the presidential chair of the Royal Society of London. And as Faraday put it in a rather unstated way, they were never in the same state of relations after that than before that. Wollaston, who's one of those people who sort of has great hauteur, simply sort of ignored Faraday and said, right, if you want it, you can have it. I'm not going to fight you for it. 10 years later, Faraday made the discoveries for which he is still renowned, particularly in the science community, that of electromagnetic induction, whose electromagnetic induction ring, and with the first electric generator there. Now, it's quite obvious on theoretical grounds from Ørsted's work in 1820 that induction must exist. People have been looking for continuous phenomenon. Faraday's great insight into induction was that it was a transient phenomenon. And this is still one of the things nobody quite understands why Faraday decided to build this device, which takes 10 days to build. I mean, students of David Gooding's built this device exactly as Faraday would have to build it. It takes 10 days, a huge investment of time for someone who's as busy as Faraday. In terms of the continuous idea of induction, Jean-Daniel Colloiden in Geneva in mid-1820s, got a device very similar to this, but he kept his battery in a separate room. So by the time he got and turned the battery on and got back to the experiment, the phenomenon had been and gone, and he missed being famous. There's a moral there about how you do experiments. One of the consequences of Faraday's discovery of induction is that he showed that electricity could be generated from magnetism. And the question that immediately arose was this electricity the same as the electricity you got from electric static generators, such as the one Rob illustrated? Was it the same you saw from lightning? Was it the same you got from torpedo fish? And Faraday started a series of experiments to show that all electricity, no matter what its source, was the same phenomenon, in the course of which he started to realize that Davy's theory of electrochemical action, which took place at the poles of something undergoing electrochemical decomposition, was simply not valid. And so Faraday did this really, really clever experiment, and that is he made a pole of water. And that showed showed two things. First of all, that poles did not have to be metal, and secondly, it showed that the action occurred in the material undergoing decomposition. And Faraday very, very quickly developed this theory where he showed the different atoms going to the different poles. And he stopped calling these poles. These now became electrodes, a word he introduced into chemistry, but he really very quickly abandoned this because he realized that Faraday didn't really believe in atoms, and he suddenly realized he was still stating some sort of atomic theory, and so he retreated very, very rapidly and abandoned that as one of his more embarrassing papers, which he never ever refers to again. Also in the course of this work, which involved in correspondence with William Hill developing words like anode and cathode and ion, he also observes what we now call semiconduction. But it's such an odd phenomenon that he doesn't quite know what to do with it. And so what the Faraday does is in his laboratory notebook, when he sort of finishes writing up his paper, he puts a pencil line for it. This here discovered with the observation of semiconduction and sulfurate of antimony, he doesn't know what to do, and there's no pencil line, and it's not published until his research notebooks are published in the 1930s. And in 1836, he develops the Faraday Cage, in which he argues against electricity being material in nature, but is actually a force. Is any of that revolutionary? Or is it just sort of, or is it, as I would suggest, actually evolutionary, so sort of building on experiments, interpreting experiments according to Faraday's immaterial theoretical views? Now, by the end of the 1830s, Faraday had two problems. First of all, what was the nature of matter? Faraday didn't deal with small problems, he just got on with big ones. And secondly, why wasn't magnetism specific to all types of material? Until this time, only iron and nickel were known to be magnetic, and Faraday could not proceed with elaborating any of his theoretical ideas of the field, as he came to call it, until he could solve this problem. And for the following 5 years, throughout the 1840s, he concentrated a huge amount of effort in showing that magnetism was a universal property of matter, akin in that regard to gravitation. And he did it using these pieces of apparatus in the autumn of 1845. Placed a piece of heavy lead buoy glass on top of a very powerful electromagnet, passed a very plain polarized light through the glass, turned on the electromagnet, and so the polarization of light changed. The Faraday effect, as you sometimes see it called in textbooks. And then a few weeks later, end of October, beginning of November 1845, he built the world's most powerful electromagnet, placed a piece of heavy glass within a cylinder to stop drafts, and turned it on and showed the glass aligned itself along the lines of force of the electromagnet. And a wonderful couple of days in 1845, when he sort of could lay his hands on glass, crystal, metal, umber core, lump of beef, 50 or 60 different types of material he showed were all magnetic. And thus magnetism was a universal property of matter. And this allowed Faraday to formulate his field theory of electromagnetism. And this he did in a slightly peculiar way in a lecture given at the Royal Institution in April 1846. These are his notes. That's it. That's all there is in the notes. The published version in Philosophical Magazine comes to about 4 octavo pages. And Faraday, who doesn't only believe that electricity is a force, not a fluid, doesn't believe in atoms, doesn't believe in matter, he also doesn't believe in ether. Faraday doesn't actually believe in very much, apart from God, so far as I can make out. And in this, he says, so inclined to dismiss the ether, the imponderable material that was required to transmit light waves. And from this, Faraday developed his iron filing diagrams, and we've sort of heard from Rob about early iron filing diagrams. And this is my favourite photograph of Faraday. It just shows Faraday holding a magnet in the mid-1850s, and I always caption it as Faraday attracting the world because it's an entirely symmetrical phenomenon. And again, on the basis of his career, Faraday became pretty famous. He appeared on the £20 banknote, and he also had one of the very few scientific figures who has a statue out of doors in London by Waterloo Bridge. And it was the old Waterloo Bridge by Telford, which Faraday in 1832 did his early magnetohydrodynamic experiments. So there's a sort of nice appropriateness about the location of the statue. Part of Faraday's theory was mathematized by very young William Thomson, later Lord Kelvin, and it was then taken up by James Clerk Maxwell, who had a sort of slightly checkered career at Aberdeen and at King's College London. Slightly checkered because he couldn't lecture particularly well by all accounts. I don't think his Scottish accent helped either, one has to say. And he writes this paper in the mid-1850s on Faraday's lines of force, where, as you can see, he starts using differential equations. He sends it to Faraday, and Faraday's response is, I was at first almost frightened when I saw such mathematical force made to bear upon the subject, and then wondered to see that the subject stood it so well. And then he asks, could not Maxwell express in common language as fully, clearly, and definitely as in mathematical formulae, translating them out of their hieroglyphics, that we might also work upon them by experiment? Unfortunately, we don't have Maxwell's response to Faraday calling his equations hieroglyphics. But the interesting thing here is that Faraday thinks it's only by putting things in common language that you can actually then start designing the experiments to see how they work. Maxwell was had huge admiration for Faraday, writing to a friend of his that Faraday had produced the nucleus of everything electric since 1830. And in particular, Faraday's thoughts on ray vibrations, that one-page lecture of 1846, Maxwell commented, the conception of the propagation of transverse magnetic vibrations to the exclusion of normal ones is distinctly set forth by Professor Faraday in his thoughts on ray vibrations. The electromagnetic theory of light, as proposed by him, is the same in substance as that which I have begun to develop in this paper, this is 1865, except that in 1846 there were no data to calculate the velocity of propagation. Now, Faraday, to his own satisfaction, though not to many other people's satisfaction, I have to say, had got rid of the ether. Maxwell had shown that you could actually sort of self-propagate light, but because he was so thoroughly inculcated with the sort of Cambridge view of mathematical natural philosophy, he retained an ether, made a sort of really very mechanical version of the ether. And it's this kind of diagram that drove people like Pierre Duhem quite wild when they criticised British natural philosophy, British mathematical natural philosophy at the end of the 19th, beginning of the 20th century. So in some ways you could argue, I'm not sure I would argue, but you could argue that part of Maxwell's work is actually going back because it's restoring the ether, and even worse, making an ether a mechanical device with cogwheels and so on. But Maxwell became very famous. Although you wouldn't believe that from the number of newspaper cuttings that are sent to me by colleagues of mine north of the border with the headline saying Scotland's unknown hero. I mean, it's just extraordinary how many people still think that Maxwell's not known, which is nonsense so far as I can see. And he has this wonderful statue of his dog in Edinburgh, which was unveiled a few years ago, and Maxwell's equations are on the back of it. So what are we to make of all of this in terms of paradigms and notions of scientific revolutions, which are possibly revolutions based only on theoretical understanding, with limited understanding of practice, materiality, institutions, and all the other things that people like me spend lots of time studying? Well, Einstein had huge admiration for both Faraday and Maxwell. Einstein had 4 portraits on his wall in Princeton: Galileo and Newton, and Faraday and Maxwell. And in 1940, he wrote that he'd taken in Faraday's ideas, so to speak, with our mother's milk, which is a really quite extraordinary thing to say, but never mind, that's Einstein for you. More important from what I want to say is that in 1936, when he read an article on physics and reality for the Franklin Institute, he said, "The electric field theory of Faraday and Maxwell represents probably the most profound transformation which has been experienced by the foundations of physics since Newton's time." I've highlighted quite deliberately the word transformation because what I want to suggest is that instead of scientific revolutions and paradigm shifts and all that sort of language that's sort of grown up since 1962, if you start burrowing into the detail of how these people did their work, lived their lives, a lot of these grand narratives just disappear. I've just got a paper coming out in which I dispute the existence of anything called the Enlightenment, because again, if you sort of start looking at the day-to-day lives of people, these things aren't there. They're at the level of grand narrative, they're at the level of historians' narratives. There's something historians have put onto these people, and it might not actually bear any representation to what actually happened in the laboratory or in the study or in the field. And so instead of scientific revolutions and paradigms, I would like to adopt Einstein's idea that we understand physics in terms of transformation, in terms of gradual evolution through experiment, through theory, through understanding, through just plain hard work. So, thank you.
So we've flip-flopped a couple of times. That's only the first 3 talks. There's 2 more to come after lunch. I'm excited to see what's coming to follow. So questions for Professor James? Yes, at the back.
Hello, I'm a lay person. I'm not a philosopher, I'm not a historian. I've done a little bit of science. So my question to you is controversial, and I enjoy being controversial from time to time. You rely, in everything you obviously stated there and the other 2 speakers, on the hardcore scientists. So you get a lot out of the hardcore scientists for your work. Can you think of any examples where the reverse has happened, i.e., if I use the previous speaker's book, Kuhn, has any hardcore scientists ever said, I read Kuhn the other day, and therefore this is what I'm going to do in the lab?
Not that I can think of, I have to say. Rob? Yeah. They're very popular, that's right. They're very popular, but not Kuhn, which is quite... I mean, people, someone like Peter Medawar, who's a very distinguished Nobel Prize-winning physiologist, was explicitly Popperian. When he founded the Medawar lecture at the Royal Society of London a few years ago, Popper was the first Medawar lecture. And I actually happened to be able to get into that lecture theatre just about, because it was totally crowded to hear Popper. And one of the things that Popper sort of gave 10 propositions about the sort of physicality of biochemistry. And he said that it was impossible to reduce biological phenomena to physical phenomena. And at the end, somebody got up and said, why do you say that? in a thick Viennese accent. Unfortunately, Popper, who was very deaf at this point, didn't know who was actually asking this question. And George Porter, who was chairing it, had to go and repeat the question. And Popper said, "Go away and think about it for 10 minutes," also in a thick Viennese accent. Unfortunately, the person who asked the question was Max Brooks. And the following week in New Scientist, Brooks wrote a 4-page diatribe, pulling Popper to pieces for that really rather silly statement, has to say. So there are some scientists who pay attention to philosophy of science, but it's mostly some people like Popper. I cannot think of any scientist quoting Kuhn in any kind of meaningful way like that. But there may well be. I mean, that's just a function of my reading.
There are plenty of contemporary scientists who have actually dismissed philosophy as being of absolutely no value in helping guide experimentation or even helping shape theory. I would like to point out that based on my researches, for the most part, these scientists are also very heavily engaged in aspects of philosophy, even though they might not know it. Any more questions? Yes, one here.
A comment, really. Yes, just a comment really rather than a question to all the three speakers this morning. It's struck me again how, for example, Newton and Hooke, how Hooke had the qualitative insight. He wanted to get at the what you might call the structural aspect. How does something happen? And people, characters like Newton, were inspired by that, and they had that kind of abstract skill, the mathematical skill, and really I'm just struck again by how the fusing of those two impulses really creates the transformation or the paradigmatic shift. Thank you.
I mean, I think there are sort of issues in there about what you actually want to prioritise in terms of our understanding of science. And the problem I have with Kuhn, writing in 1962, is that he prioritises theory above all else. I mean, he recognises experiment and observation are there, but they're simply there to inform or disinform theory. What people like me have been doing in the past few decades is sort of create a much more holistic, much more contextual view of how science is practiced. And so Joseph Banks, for example, Banks is another person who gets absolutely zero rating in Kuhn's book. You would not imagine writing a history of science in the late 18th, early 19th century without mentioning Banks, because Banks is such an important patron in getting things done. So it's those sorts of changes that have happened in the history of science over the past 40 years.
Okay, do we have any more questions? One last one, perhaps? Okay, that makes me privileged so I can ask the question.
Yeah.
So, let's it's always been a puzzle of mine that Faraday was a Sandemanian, and Sandemanians prize themselves on their literal interpretation of the Bible, that's my understanding. And Faraday always claimed that he was reading the book of nature, but is there anything, Professor James, you could share on your studies of Faraday that would give us some insight into how he thought, how long his approach to the work there? Just, you know, the usual scientific soundbites would be good.
So Faraday is fully committed to this sect throughout his adult life. He made his confession of faith in the church in the 1820s, a deacon in the 1830s, an elder in the 1840s, again in the 1860s, in which world we baptise babies and preach sermons. And I think the only way you can actually understand Faraday's science and the way Faraday's science goes is by seeing it as an intense theological exercise conducted in the basement laboratory Royal Institution and the study upstairs. And it has, that religious commitment has all sorts of effects. So from the sort of mundane, so Faraday could not go to university because both Oxford and Cambridge until the mid-19th century would only allow Anglicans to study and sign then article of faith to come to this place. To Faraday's this belief in matter and atoms and ethers and all of that. Now, Faraday's theory of the field was predicated on the assumption that instead of atoms immersed in a luminiferous ether, let's imagine instead a mathematical points distributed throughout space, and what we see as a particle in space is simply a combination of lines of force meeting at that point in space. Faraday is very, very clear on this. We only know matter by its forces. Now you can actually turn that around. It means it's entirely symmetrical with the other idea, where actually forces are a consequence of matter. But because of Faraday's religious beliefs and therefore lack of belief in matter, he took that interpretation. There's that interpretation of the field, and that actually unlocks the solution to all sorts of problems from the 1850s onwards that have been coming to the fore in theoretical physics in the sort of 1850s and onwards, which simply could not be solved by more traditional material, actual distance mathematical theories. And so Maxwell, in a profile of Faraday, which was in 1873, in Nature, is really interesting on this, because Maxwell says, yes, Faraday didn't know analytical mathematics, but he was actually a geometer of a very high order. And Maxwell says if you write your work in geometry, which is what Faraday did, you can then write it in analytical mathematics, which is what I've done in my treatise Electricity and Magnetism. And Maxwell's very clear on that Maxwell was sort of the really great mathematical natural philosopher of the mid-19th century. Is very clear that theory does not equate to mathematics. You can have theory in terms of language, which is what the point Faraday was making in his hieroglyphics. I actually just thought of that. I mean, maybe that's Maxwell's response to Faraday's hieroglyphic claim. Thank you.
Thanks very much.